So we are in week 7, our midterm exam, which we've now hopefully done a bunch of thinking about, is 6 days away. There we go. Forgot to turn on my key light. So Monday evening. So today we will be wrapping up we'll talk about the midterm procedure stuff, and then we will also talk about the last topic, which will be included on our midterm. Excuse me. All right, that's better. Our last topic for the exam, which is matrices, not matrix elimination, but all these other matrix operations. We started talking about them and we looked at matrix addition and subtraction, talked about it briefly, but today we'll finish all of that. We'll do some more practice with that in tomorrow's class, Thursday's class, and then we will also do some review about some earlier concepts from the semester. But the one big topic for the exam is all these matrix operations, which we're doing today and tomorrow. Another big one is linear programming, which we just finished spending a whole lot of time on. And I'll do a little bit of review, just discussion review about that today. And then matrix elimination, break-even points, systems of inequalities. Those are kind of the other bigger things. So we'll do some review about that stuff on Thursday's class. But I'm not going to do additional review about linear programming because we've just finished it. Okay. So the tight constraints, slack constraints, I'll review again with the example that we had last time, what exactly those concepts are. Hopefully we're kind of remembering those ideas. We got to matrix addition. We didn't do scalar multiplication, but we will do that today. Okay. First though is exam stuff, or homework is almost entirely graded. We're very close to being ready to return that. 1 or 2 people had to make some adjustments. The midterm, like upload your photos and all that kind of practice stuff, I finished that, returning and commenting on all that stuff for the other 2 sections. Your section is the only one I didn't have time to get to yet. So that will be a bit later today. But you guys probably have lots of questions about that. So let's get into that. Again, I haven't looked through all the ones for your section yet, but for the other sections, one of the things in the practice midterm was, tell me like what parts of this you don't like or you're concerned about, the question 4 for that. So reading that, I'll give some discussion, or I'll answer some of those common concerns. Scanning and the timing, I have another slide next where I'll talk about that. The no calculators rule, yes, really no calculators, sorry, but that's not going to change. The numbers will work out fairly nicely, or if there's a very difficult calculation, I'll just give you the number. Hey, guess what? This number, I don't know, cube root of 7.62 or something. Hey, guess what? It's just, here's the number. You might need this at some point during the exam. So if it's a really hard thing like that, I'll just give it to you. So again, calculators should not be necessary. The numbers should work out fairly cleanly. If you like really need a calculator, you're really struggling with something, you have almost definitely made some kind of mistake somewhere. Lots of people ask me or want to ask how many questions are on the exam. I don't yet really understand what the intent is of the question, why you think that would be helpful. you know, because it could be one question with like 20 parts or something. Like I could make the exam that way. I could have 20 tiny little questions or 100 little questions, or I don't know. So I don't know why that's that useful. I will cover everything that we have done so far in the semester. So there's no like guessing game. Will it be this or will it not be that? So all the skills we've been working on will be tested, and you will probably be busy for the whole exam. Don't expect to finish like really early. Yeah. So a few more things, again, to address some concerns, and then I'll open up the floor to whatever questions you want to ask, and then we'll go from there. So side view, scans, the selfies. So you've submitted that for the practice midterm thing. If you haven't submitted this, most people have, but if you haven't, then do that. If I can't know for certain that you are familiar with the policy and you're going to submit your work in an organized fashion and you know how to set up your cameras, then I'm not going to be particularly motivated to accept your work. This is you showing me that you're ready for the midterm. So please do this. And it is worth points for your homework. So if you do this, it's just free points, not hard. Okay, timing. I said before that the exam would be 2 hours. I've been thinking about that, and some people said, oh my God, 2 hours is very long. Final exam will be 2 hours, but the midterm will be an hour and a half. So I've decided to make this a little bit shorter. Hopefully nobody is upset with that. So you should, I said, be available from 6:30. You get your camera set up or anything from about 6:45, 6:50. I'll open the Zoom session and I'll give some final comments about reminders about rules or whatever. We'll actually formally start at 7 o'clock and then finish at 8:30. So 8:35 will be the deadline to submit all of your scans, your PDF with all your pages. And then 10 minutes past that will be the deadline for submitting the selfies. If you think you need more time to scan, then start earlier than 8:30. If you think you need 1 more minute, then start 1 minute earlier. If you need 5 more minutes, start 5 minutes earlier. Scanning really shouldn't take that long. So you're probably using your phone as the side view camera. So using that phone for scanning your pages is fine. So the side view camera will disappear when you start doing your scanning. That's what I'm expecting. But that's why we're saying within a certain amount of time. If you're spending like 20 minutes, 30 minutes doing just the scanning, then we become extremely suspicious about something else happening. So at most 10 minutes is what you would need. But if you are taking more than 5 minutes, I will start asking you what's going on. Tell me exactly what your technical problem is that's causing a delay. So practice with your scanning apps. For nearly all of you, you'll be able to finish within 5 minutes. If you do feel you need more time, you're welcome to start earlier. Okay, that's scanning selfies. Also, lots of people complained about this, but yes, necessary. They are a major step of sort of confirming that you are actually the person doing the work that you have submitted. Some people suggested just like a signature on the page. I don't know all of your signatures. Like, should I ask everyone to send me a photo of their signature and then I analyze the handwriting or something? Your face is a much easier and more reliable thing to identify. No one else is going to see your selfies. They're going to sit in the folder. If I if we suspect something, if we have to confirm that you indeed did your own work, then we'll go look at the selfies and compare those pages with your actual pages. Otherwise, like, I don't put the selfies on like Snapchat or Instagram or whatever. So privacy, all that is maintained. During the exam also, no one else will see your camera feed. There's an option in Zoom, which I could turn on right now to show you, but all of you have your cameras off anyways. So no other camera feeds will be visible. You can only see the host, me, and only the host can see you. All other cameras will look blank or look off to you. So privacy is maintained in that regard. Selfies, looking at the selfies, lots of people took the selfies from like really far away, and like they and their pages were actually a very small part of the photo. Hold the camera closer, just the whole page and enough of your face that it's recognizable, but you don't need all kinds of like blank space around you. So take the selfies closer up. Side view camera, lots of people, I don't know why, but lots of people had the side view camera arranged like vertically. Turn it to the side so that we can see the face and the full monitor that you're looking at. The camera can be closer. It's easier to set up that way. I have no idea why lots of people did it vertically. In the photos as well, I could see like from the location of the camera where the photo was taken, like you had like a friend or a roommate just standing there taking the photo. That's exactly not what I want the photo. Like, find a place to actually set your camera down. Your friend is not going to stand there for an hour during the exam holding your side view camera. So find a place to actually mount your phone, and your side view camera view should show that. If it looks like someone else was holding your phone for the photo you submitted, I'll tell you to set up your phone properly and then redo it. Two more things. Okay. If you are a student who is in China right now, if you're a Chinese student in Korea or somewhere else, you have access to Google stuff, no problems. But if you are currently in China and will be for the exam, then after class, tell me who you are or write me a private comment right now in the chats, and I will have a backup method in case you have trouble accessing the forms and stuff. But I need to know who exactly those people are. Okay, last one. Roommates. In the past, it hasn't really been an issue for people to just find a different place, or some people just did the exam on campus. But lots of people are saying that there's an issue with this. So I thought about this, made an adjustment. Please try to find a different place or a separate physical room to do the exam. If that is not possible, if you have a roommate who is not a student in this course, then you should be telling me their name and their student ID, and I will look up the ID and I will confirm that they are not a student in the course. And then, okay, you should not be talking with that person or interacting with them in any way during the exam. If your roommate is a person in this course, again, I very much want you to find a different place to do the exam. If that is not possible, then tell me in advance. I've made a Google Forms thing. I'll share that just after class, or sorry, in the afternoon. You need to tell me in advance. And the other students, the background of your front camera view, like you should be able to see the person, like just sort of in the background, and I can see that they're, far away from you, or the other side of the SolGeo room, and that you are not like, turning around and talking to each other. And then if one student finishes the exam early, then they should stay in Zoom and at their desk until the other person is finished as well. And then once both students are finished, both students can leave. So that's the compromise. I think that's a reasonable and not too hard way of managing things if you do have a roommate who is in this course. Okay. All right. That's the concerns. That's everything I was reading. So let's go. If you have any questions about the midterm or what's happening, please ask. No questions? Everything's clear? No one has concerns, confusions? Okay, if so, that's great. That makes things easier for us, for sure, if everyone's clear about it, but yeah, nothing. Okay, well then, let's go on. If you do have questions, you can ask later in the class. So let's think about last time. So we had this linear programming question, and we had this whole thing about 2 different kinds of gates that some company is making, and they have these 3 different constraints here that they were operating under. And we had 2 different objectives, one for maximizing revenue and one for maximizing profits. How can we accomplish each of those things? So we did our whole linear programming method here, and we drew our situation. We had a first objective here, this green line for revenue, and we determined that C is the best point here, is the best corner optimal solution. And then we did the same thing over here for the profits, and we figured out that B is the best corner, the way to optimize profit, maximize profit here. Okay, so the tight constraint and slack constraint ideas, we'll just review those briefly here. First, point C, which constraints are maximized? Which constraints are fully used at point C?
Finishing and administration.
Okay, good. So just finishing and administration, because it's the blue and purple lines that are intersecting at point C. If our corner is on those lines, that means we are at the limit of those lines. We can't go further. So welding, then, what about welding? Are we over our limit for welding or under our limit?
Under our limit.
We are under the limit. So we had 840 welding hours available, and we are somewhat under that. We can see that on the graph because there's a gap here between the orange line and the corner that we have identified as the best one. That gap represents we are not at that limit. There's space, there's some extra, there's room there. And we did the same thing for profits, and we saw that for B, which is the best point for profit, it's welding and finishing, orange and purple lines intersecting there. So we have this distance between admin and point B. And so we have unused admin labor hours available there. So if the constraints are meeting at that point, we've used all of the constraints available. We're using all of the 300 and all of the, this one, welding, 840 hours available. Those are tight constraints. Tight, again, as in like trying to pull a rope. It's now tight. There's no more to pull. We are at the limit. So it is a tight constraint. The other one, admin, is what we call a slack constraint, because we had 250 available. We didn't use all of it. Again, like pulling a rope, it's slack. There is more to pull. There is more available if we need it. So that is slack. And we did some calculations with this, and we saw that we had 140 unused welding hours, 70 unused admin hours for each of these solutions. So when we maximized revenue, if we take the corner, the way that we maximized revenue, which was 200 basic gates and 50 fancy gates, if we put that into the finishing constraints, it will turn out to be exactly 300. That's what our graph showed us. If we put this into admin, it will turn out to be exactly 250. Again, we saw that from the graph. But if we put that into our welding constraint, the slack constraint, then the actual welding hours used will be less than this, less than 840. So in our case, it turned out to be 700. And then how many are extra? Well, just 840 minus 700. That's the slack amount. That's the extra amount available. And exact same thing for admin. It turned out to be 180 hours needed for that one for maximizing profits. 250 minus 180, 70 hours. So we can see from the graph exactly which ones are tight or slack, whether a constraint is tight or slack. And then we just take that corner, those values for the corner, and substitute them into the slack constraints. And we can figure out exactly how much is needed and therefore how much is extra. So that was the last kind of extra thing that we did with these problems last time. Okay, so let's just do a little kind of summary discussion about where we got to with linear programming. So we had problems with 2 constraints and we had problems with 3 constraints. If we had a problem with 4 constraints or more, 5 or 6, those would still be possible. We'd have our 2-dimensional graph, but we would have a few more constraint lines, so our shape might be a little kind of more complicated, a few more corners. But overall, it would not be too difficult. It's still possible. It's a little more setup work. If we had lots of objectives, so maximize this, minimize that, etc. 1 objective, we did that. 2 objectives, we did that as well. Still quite possible. 3 objectives, sure, it's just a little more work. It's yet another corner to find, but it's still doable. 4, 5, 6. Again, a little more work, but it's still, we don't have to change anything about our method. On the other side here, variables. All of the problems that we did had exactly 2 variables. If we had 3 variables, something major would need to change. Does anyone know how our solution method would change, or how would our graph change? How would it look different?
It has to be.
Okay, 3-dimensional graph. It would look something like this. And this is the thing that is done in some classes. We will not be going there, but this is a 3-dimensional feasible region. So it's not a line for the edges of it. It's planes, big flat sections, and all being combined. We're not going to do problems like that. They are possible. There's a method called simplex, which will help solve problems like that. So this is sort of a more complex version of linear programming. If there were 4 variables, 5 variables, 6 variables, what would happen? What would need to happen? Yeah. 4 variables would require a 4-dimensional graph. Our human brains cannot visualize or conceptualize a 4-dimensional graph. Well, I can't, at least. If you can, let me know. I'll introduce you to some math people who will be very interested. to study U. So it's kind of impossible. Or 5 variables, 6 variables. In that situation, we have to find just, you like write a computer program that will solve these for you, because they get way too complicated at that point. So increasing variables makes the problem a lot harder. 3 possible, but 4, we need a completely different method. Non-linear functions, that's the other possible wrinkle or a challenge here. For non-linear functions, so not straight lines, not everything we want to maximize or minimize involves straight lines. So if we had multiple variables, 3 variables, we'd get something like this. 3-dimensional graph, and we have these like curved shapes and all these things happening. This here is called a saddle point in the middle. So it's the lowest of one thing while maximizing these other whatever. So that kind of thing can happen as well. That is solvable. That's a thing called unconstrained optimization and constrained optimization. But to do that, we need calculus. And in this course, we are not there yet. We don't have calculus yet. So we'll do the introduction to calculus at the end of the semester, but this kind of problem with calculus is harder and we won't be quite there. So that's where this kind of optimization process can go and how it gets more complicated and what other tools we might need. But this linear programming thing, it's a nice introduction to this concept of how to optimize and maximize something or minimize something. And then this is how it often ends up working in the real world. Okay, let's go back to matrices. So again, we've started this a bit. We'll talk some more about all of this. Let's see if we remember measuring dimensions for a matrix, the size of it. How do we measure dimensions?
Row multiplied by a column.
Okay, rows, then columns, rows by columns. So in this case, we have a 1, 2, 3 rows, 2 columns, so a 3 by 2 matrix. The order, rows first, then columns, is very important, and we will understand why when we get to matrix multiplication today. To be equal, if we say 2 matrices are equal, what things must be true about them?
They have to have the same number of rows and columns.
Okay, so same dimensions. And that's not the only thing that needs to be true. What else?
Numbers.
Okay, so all the same values should be inside the matrix. One more.
On the same places, like the
All-
same numbers in the same places.
Right, so all the same values in the same position. So everything must be equal about them. If there's any difference whatsoever, the 2 matrices are not the same. So we can't say that they are equal. So very strict conditions on that. Null matrix or 0 matrix. What does this look like?
Every value is 0.
Every value is 0. And what sizes can they be? What dimensions?
Any dimension.
Anything at all. So if the matrix is all zeros, then that's called a null matrix or a 0 matrix. An identity matrix, what does that look like?
It's a square.
Okay, square. So the dimension row, the number of rows and number of columns must be equal. And
The variable is 1.
variable is 1. I want you to be a little more precise. It does involve ones, but something else about it.
One's in the main diagonal of the matrix.
Okay, so one's in the main diagonal. and everything else is 0. So it must be square, does not need to be 4 by 4. It can be 5 by 5 or 2 by 2 or anything, but we'll have 1s in the main diagonal and 0s everywhere else. When we talk about addition and multiplication today, we'll see exactly why we care about these two things. Okay, so those are the properties, 2 important properties and 2 types of special matrices. So let's review the transposition and do some addition, subtraction practice, and then we'll get on to the multiplication ones. So I think these are the same numbers we had last time. Let's just do this again, make sure we remember. So let's say first we want to calculate C transpose. If this is, I'll ask you, matrix C here, what are the dimensions of it?
3 by 1.
So 3 by 1. So if we are going to do C transpose, what will the dimensions be?
1 by 3.
Okay, so it's a 1 by 3 matrix. And tell me what this matrix will be.
5,
Mhm.
-6, 15.
And 15. Okay, so we did not rotate. It might look like a rotation, but let's do the next example and we'll see how it's different. So we have a 2 by 3 matrix for F. So if we do F transpose, what will be the size of F transpose?
3 by 2.
All right, let's see. 3 by 2. Tell me the first row, or let's do first column of F.
0, 2, 2.
2 and second
105.
105. Okay. So we can see from this that we did not rotate. This is not a rotation if we compare these two. This is not just rotate to the side. We've done a diagonal flip. We took the first row and we rewrote that as the first column. Then we took the second row and we rewrote that as the second column. That's what we have done. It's a full diagonal flip. So that's the method. Take each row, rewrite as a column in that same order, and then you're done. The transpose stuff, again, we will need that in a moment. I know I keep saying that, but it's true. All right, we did the other one before, so I'll skip that one and we will go on to our next topic. So not rotating, flipping. Okay, addition and subtraction, and we talked about this. We had some a question on this for the homework, so we just let's review the conditions here, and we'll go through these examples and see what happens with these. So matrix A plus matrix F, is that operation possible?
No,
No.
it's impossible
Why?
because their dimensions do not match.
Okay, so A is a 2 by 2 matrix, F is a 2 by 3 matrix, 2 rows, 3 columns. If the dimensions don't match, we just stop, and this is an undefined operation. Undefined. All right, let's try the next one. So A plus G, is that operation possible?
Yes, it is.
Okay, so G is a 2 by 2 matrix also. So let's actually do that. A plus G. The numbers are not especially hard here, so let's, yeah, I'm not going to write out A and G separately down here. Tell me what the first row would be of our resulting matrix.
4,
Mm-hmm.
3. 0.
4, 0. And next
Three.
row,
4.
3 and 4. So the first position, we just match up the positions. 1 plus 3 is 4, done. 2 plus -2, 0, done. 3 or -2 plus 5 is 3, and 4 and 0 is 4. So just match up the corresponding positions, add them together, and that's it. All right, let's look at another one. Let's look at question 3 here. G plus A. What do you think the result will be?
The same.
Be the same.
Same. Okay, so 4, 0, 3, and 4. This should not be surprising because if we do, 2 plus 3, that's the same as 3 plus 2. With addition, we can switch the order and nothing changes. All right, 2 more examples here. Let's do A minus G. Can someone tell me what that result is?
-2. -2.
-2.
0.
-4.
Uh,
0.
4, 4.
4, positive 4.
Yes.
Okay, and next row.
-7.
Mhm.
-7. And 4.
And 4. Okay, so the 4 here, 2 minus -2, so 2 plus 2, 4. All right, so that's A minus G. Let's do the other one. So G minus A. What do we think that result will be?
2
Mm-hmm.
minus -4.
Mm-hmm.
7.
Okay, positive 7 here
And
and
-4.
-4. What do we notice about the two results? About this one and this one?
Inverse
Opposite.
of each other.
They're
Okay.
opposite.
So yeah, they're the same thing except all the signs have been flipped. So A minus G is equal to -G minus A. So just flip the signs and then you'll get the same thing. So that should not be surprising. 2 minus 3 is equal to -1. 3 minus 2 is equal to +1. So it works the same way as regular addition and regular subtraction. So no surprises there. So pretty straightforward matrix addition and subtraction. I'm drawing attention to this to help highlight the fact that matrix multiplication is going to be super weird. So I know you could figure this, like see the connections on your own rather easily, but the other thing we're going to look at, matrix multiplication, does not follow these kinds of rules. All right, so that's the addition and subtraction. Scalar multiplication is not hard. It's also straightforward. So just terminology here. Scalar just means like, scale up or scale down. So basically just think of kind of like a coefficient. We're just taking some constant and multiplying it by another thing. But the other thing is not a variable. It's this big matrix. So we call it a scalar instead of a coefficient, but more or less the same concept. Okay, so that's where the term comes from. Scalar multiplication. It'll be something like this, where we have a matrix A and we want to do the operation 5 times A. So if we do 5 times A, that can we take a guess? What do you think we would do to do scalar multiplication?
Every component needs to be multiplied by 5.
Okay, so just each position multiplied by 5. So 5 times 1, 5 times 2, 5 times -2, 5 times 4. And so that just turns into 5, 10, -10, and 20. That's it. So scalar multiplication, also not hard, not surprising. Just multiply each value by whatever position. We could have things like this. Excuse me. So 4 times I. If you remember, I is our symbol for the identity matrix. If I say 5 times A is just some matrix. We don't know what that looks like. It could be anything. So they have the, the person should tell us, oh, this is what matrix A is, by the way, here are the values. We don't do that. I is a special letter. It's reserved only for the identity matrix. So matrix I always means identity matrix of some size, and that should be obvious from the context. So it's not some random thing. It always means identity matrix. And then here we're saying when the identity matrix is a 3 by 3 matrix. So 4i would mean 4 times this matrix here, 1, 0, 0, 0, 1, 0, 0, 0, 1. So that's a 3 by 3 identity matrix. So can you tell me what the result will be?
4, 0, 0,
Mm-hmm.
0, 4, 0,
Mm-hmm.
0, 0, 4.
Okay, so again, just multiply each position by whatever the scalar is, whatever the number is on the outside, and there's your result. So scalar multiplication, also not tricky, not surprising. Okay, let's give people a moment in case they're writing something down. All right, let's go on to the weird one, which is matrix multiplication. So I have a definition of it here at the top. So I'll explain exactly how we get to that. I will tell you how we will use this. We'll look at some examples. We'll get some practical examples. We'll get to that in the next class. But before I can tell you why it's useful, I first have to actually tell you what it is so that I can show you the uses. So it's going to feel really weird, but we'll get through it. It's not terrible. It's a little weird, but it's certainly learnable. So the idea with matrix multiplication, we do not just like match up the corresponding values and multiply them. We do some kind of big thing for each position here. So the process is we take each row of the first matrix and we multiply that by each row of the second matrix. Not only the first one times the first one, second times the second, third times the third. We take the first row, multiply it by every, sorry, let me mute. Forgot to mute that alert. There. First row of the first matrix times every single column in the second matrix. Then we go to the second row of the first matrix and again multiply by every single column in the second matrix. And then the third row in every single column. So if it's a big matrix or two big matrices, it's actually a lot of steps involved. So let's go through that here. So at the top, our first matrix, our example one is a 2 by 2 matrix. Our second one is a 2 by 2 matrix. And in this case, our result is also a 2 by 2 matrix. We have 1, 2, 3, 4 positions here. They won't always be the same size, but for this first example, they are. Okay, so we need 4 positions, 4 values. We will get to them by doing this. Sorry, I forgot that I had that on the slide. There. 4 big steps. The first step is, as I said, the first row times the first column. How do we multiply a whole row by a whole column? Well, there we match up the individual values. So we take A, the first value that we have, and then the first value here, A times E, that's here. And then we add to that each of the other positions kind of lined up and multiplied. So we also do A times E. And then we also do B times G, which we see here. Multiply those together. And then after we keep doing that until we get to the end of the row in the column. And then afterward, we add all of those up. And then that one value is the new, that's the value, our resulting value for that position. Okay, let's do another one here. So for the second position, we're still working with the first row. We're not done. We have to do each row times each column. So first row still, but now times the second column, FH. So then it's A times F, which we see here. And then it's B times H here. For the second part, do those multiplication steps. Then afterward, add together all the results. And that whole thing is just one next position of our resulting matrix here. So we might have this question, well, where do the results go? If I'm taking this whole row and that whole column, where do I choose to put the results? Well, we put them where they line up. So we can see that we have for step 2 here, first row, if we highlight where that first row is in our resulting matrix, we see that's highlighted in blue here, like this. And then we see that we have the second column of the second matrix. So just kind of highlight there. And where do they overlap? There's only one position where those two things will line up. That's where the result goes. So we can see it's the overlap of the two blue things here and overlap of the two red ones for the first step, etc. So we're multiplying each one position as we go, match them up and multiply, add them all together. Then where does the result go? It goes in the place where that row and that column line up in our resulting matrix. So that's just halfway done. So we have to do this all again for the next row. So for the second row of the first matrix, now we're back to the first row of column of the second matrix here, EG. So C times E, line those up. D times G, line those up. Add them together, result goes in that bottom left corner. That's our third one. And then final step, where we now finally have the last row times the last column, CF plus DH, and that goes in the final position here. So it's a lot of individual calculations that all get combined and end up as a somewhat kind of small results. So we had lots of work to do to get this, but the result is just this 2x2 matrix with 4 values. Okay, so again, I know this might look a little weird. It is actually useful and lets us accomplish things. I'll get to that in the next class. That's the process. Okay, so each row of the first matrix times each column of the second matrix. let's go through some examples with these, and then it will be a little more clear. Let's start off here. So I want matrix C, A times matrix C. So here's A and here's C, same values we had before. And let's try to multiply. So matrix A times matrix C. There are lots of ways that you can write this to help you organize it and make sense of it. Lots of different ways that this is taught. I have a particular way of doing this that I think is good for beginners because it makes it harder to make mistakes. It's easier to know where everything should go. So I'm going to show you that method. If you want to write these out with some other method, that's fine. Matrix C. You can do these whatever way you like. But again, if you've never done this before, I will recommend this way. I'm going to write my top matrix really wide here because I'm going to need some room to write. All right, so let's do this. We have a 2x2 matrix with A and a 2x2 matrix with C. So our resulting matrix, in this case, it's not hard. It's going to be a 2x2 matrix as our result. I'm going to put the first matrix here on the left, and then the second matrix up here on the top. And that will help us line things up. So when we do our multiplication, we will have, so in the first position, or sorry, let me highlight again how this will work. So 2 rows, 2 columns. And we can see these overlap points. So 1, 2, 3, 4 points where we have overlap when we can draw these columns and rows like this. So 4 values to calculate. Okay, let's see what those are. We'll do the first one first here. So our first row times our first column. When we do this, we just match up the values again. So I'm going to take the first value times the first value. So 1 times 3. So 1 times 3, which I'll just write as, I'll write this out fully for the first one. 1 times 3 plus the second position times second position plus 2 times 5. And I already need more space. There. Okay, so all of that together is just that one position in this resulting matrix. All right, let's do the next operation, which will be first row still, but now times the second column here. What times what plus what times what? Tell me what the next position will be.
1 time -2.
Okay, so 1 times -2
2
plus
times 0.
2 times 0. 2. Still need more space. 2 times 0. Okay, so and then we'll do the adding step a bit later, but I just want to show very clearly what operations are happening here. All right, so that's the first row times each column of the second matrix. So that part's done. So now we have to go on to the second row. Let's go back to red. Second row of the first matrix, and now again times the first column of the second matrix. So our numbers here.
-2 multiplied by 3.
Okay, -2 times 3 plus
4 multiplied by 5.
4 times 5. All right, and then our last one, our second row and our second column. What are the operations here?
-2 times more -2.
Okay, -2 times -2
4 times 0.
plus 4 times 0. So those are all the actual operations that we're doing to find out each of these positions. So now that's done. And then again, lining up the rows, drawing out, oh, this row, this column very easily tells you where the result will go. So if I do the second row and the second column, where does the result go? Okay, just where those two lines line up. This is why I suggest this sort of side and top orientation if you're a beginner with this. Okay, so let's actually add these together. So our result then is, let's write this out, A times C. Don't need to write the X here. A times C is equal to, what are the actual values?
13 minus 4, -4.
13.
-2,
-2.
14, 4.
14 and 4. There we go. A times C is equal to that. So it took a while and we had to write out a bunch of stuff, but there we go. There's our result. So that's what matrix multiplication looks like. So I'm going to write that out on the side here as well. AC is equal to 13, -2, and 14, 4. All right, let's do C times A. Let's do the next one here. If you've already learned to matrix multiplication, please don't say anything. But if you have not learned this before, then take a guess. What do you think our result will be if we multiply C times A? So same matrices, and we're just switching the order.
The same
Results will
result.
be the same.
Okay, so we're guessing that it's going to be the same. Let's see what happens. 3, -2, 5, 0, 1, 2, -2, 4. We'll do this a little quicker. I won't write the this times this. We'll just do this plus this plus this for the positions here. So first row times first column. Our result is going to go in this top position here. What is our result? What plus what?
3 plus -10.
3 plus -10?
Yes.
3 plus 4, right?
4.
4.
3 plus 4. -2 times -2, that's +4. Okay. All right. And we'll do our next one. First row times second column. What are the numbers there?
6 plus -8.
6 plus -8. So -8, but I'll just write it like this so it's clear what we did. All right. We are now in the second column. So, sorry, second row, and then these two columns. I'll just put them both on there at the same time. For the first bottom left position, what are the numbers?
5 plus
5
0.
plus 0.
5 plus 0 times -2. So 0 and
10 plus
10
0.
plus.
10 plus 0. If we have a 0 when we're doing matrix multiplication, it's very nice because it makes a lot of our calculations very easy. Okay, so that's the step there. That's the work. So our actual result here, C times A will be equal to what?
7,
7.
-2,
Mm-hmm.
5, 10.
All right, 7, -2, 5, 10. What do we notice about A times C and then about C times A?
The result is not the same.
The results are not the same. They are not also like slightly different, or they're not like flipped or something. They're completely different. We have a -2 in both of them. That's just random chance. There's no like logic or reason why that happened. It just happens because of the numbers we picked by chance. So matrix multiplication, if you flip the order, you get completely different numbers. It's very different from normal multiplication with just like regular numbers. It's also very different from matrix addition, where we can switch the order. So matrix multiplication doesn't follow those basic rules. It has its own method and its own rules. It's almost maybe confusing to call it matrix multiplication. Maybe we should have a different name for it or something, because it does operate very differently. But it's not like regular multiplication. Lots of weird differences. All right, let's do another thing here. We are going to do another operation. So the next two that you see, we'll do A times B, matrix A times matrix B. So we note matrix A is a 2x2 matrix, and matrix B is a 2x3 matrix. So these are different sizes. We had an example earlier where we did matrix addition, and we had two matrices that were different sizes. And I told you the condition is they must be the same size, same dimensions, but we actually tried to do it, and then we found out like, okay, this is why it doesn't work. When we get the first few steps worked, but when we get to this step, we see a problem. That's why matrix addition doesn't work. So we are going to try to do matrix A times matrix B. Again, if you already know what matrix multiplication is, don't say anything. But if this is your first time learning this, what do you think will happen? If we try to do A times B, what result do you think we will get?
I think it cannot be multiplicated.
Okay, so we're getting a no. Anyone else have guesses?
The result will be 2x3 dimension in 2x3 dimensions.
You think we'll get a 2x3 matrix? Okay, so we got a no, we got a 2x3. Any other guesses? Zero, two, two. No, I need more space. 0, 2, 2. 1, 0, 5. All right. Well, let's see what happens. So if we try to line these up, if we kind of just do our, line things up like this, 2 rows, 3 columns. So if it works, then the result should be a 2x3 matrix, as we heard in one of our guesses. So if it works, that's the size we should be getting. So we can see that just by, side top arrangement like this and drawing the line. So lots of value to that. All right, so let's go through our process and see if this will work. So our first position, again, we just take first position here times first times first, second times second, and we write in the numbers. So what plus what?
0 plus
0
2.
plus 2.
Okay, so 0 plus 2. Does it work, or is there a problem there?
It works.
Seems like it works. We had the 1 and the 0 match up, the 2 and the 1 match up, so that seems fine. Let's do the next ones here.
2
So
plus 0.
okay, 2 plus 0 here, and the last one?
2 plus 10.
2 plus 10. Any problems so far?
No.
No, seems like it's okay. Seems like it's working. So we'll continue for the bottom one. So just line up each of these like this. All right, our first position on the bottom row, what plus
0
what?
plus 4.
Okay, 0 plus 4, next one,
-4 plus 0.
-4 plus 0, and
-4 plus 20.
-4 plus 4 times 5 plus 20. All right, so if we take all this and we actually write out A times B, 2 by 3 matrix, what are the actual numbers here? First row?
2,
2,
2, 12.
2 to 12, second row?
4,
Mhm.
-4, 16.
And 16. Okay. What do we think? It worked or it didn't work?
It did.
It did. So we can multiply, in some cases, matrices that are different sizes. It worked. So we should write this up here. A, B is equal to 2, 2, 12, and 4, -4, 16. So that's that results. So we are going to do this one more time. And for our last one here, B times A. So again, if this is your first time doing matrix or seeing matrix multiplication, please give me a guess. What do you think will happen? Now that we've seen that A times B works, what do you think will happen if we do B times A?
No, it doesn't work.
All right, you're saying it doesn't work. B. Anyone else have a guess while I am writing out the
The
numbers?
dimension will be 3 by 2.
Okay, so we're guessing a 3 by 2 matrix, and we also have a no guess. Anyone else? 0, 0, 0, 2, 2, 1, 0, 5. Matrix B and A could be 1, 2, -2, 4. Okay. So let's line up our things here. So we have 2 rows like that, and then we have 2 columns like that. So if it works, we should have 1, 2, 3, 4 positions in a 2 by 2 matrix. So if it's going to work for us, that is the size that we should expect, 2 by 2. All right, so let's do this for the first position. First position here, what plus what plus what?
Zero, -4,
0. So 0 times 1, yep. And -4, 2 times -2. So -4.
and then something.
Question mark. We have a 2 here in our first row for B. We have a 2, but in A, we ran out of values. There's nothing left to multiply it by. We're always matching these up one by one. We have a 2 here in B with no partner, with no matching position in A. So we stop. If it doesn't match up like that, matrix multiplication doesn't work. This is an undefined operation. This is undefined. So another very weird result for matrix multiplication. First, we had A times B and it worked. Sometimes we can take 2 matrices that are different sizes and we can actually multiply them together. Also, though, we see that if matrix multiplication, if we flip the order, as we see with AC and CA, changing the order can change the result, can change the numbers that we get. Even more than that, just changing the order can even change, if it's possible, So just flipping the order can go from a possible operation to an undefined, an impossible operation. So changing the order is significant. It's not an arbitrary change. We have to re-look at the two matrices and see if it's possible, and if it's possible, then okay, what would the numbers be? But changing the order completely changes things. It does not follow normal multiplication rules. Okay, so there's a little exploration about matrix multiplication. For sake of time, we'll do a wrap up here, and then the thing about the identity matrices and null matrices we'll get to next time. So changing order can change numbers, can also change the results. So that's what I've summarized here. Matrix multiplication, order is very important. So what are the conditions formally if we state this? So the dimensions can be different. It's okay if your two matrices have different sizes, but the number of columns of the first matrix must equal the number of rows of the second matrix. So if our first matrix is the one kind of on the left, and then the second matrix is the one on the top, then we're just kind of drawing those arrows and seeing if we have matches with each thing. So they should match up. Number of columns of first matrix and rows of second matrix. If those are equal, then we can do matrix multiplication. If those are not equal, then we can't do it, and we say it's an undefined operation. All right. So that might be a harder way of thinking about things. Let's think about the easier way of doing this. So matrix A here, let's say it is an M by N matrix of whatever sizes, we don't know, just some M and some N. So it goes, we have M rows and N columns. Okay, so those are the dimensions, rows by columns. And then we also have matrix B over here, which is a P by Q. P is whatever, Q is whatever. Just those are the sizes of matrix B. So columns of the first matrix, that's N, and must be equal to rows of the second matrix, that's P. So these two numbers must be equal. So doing matrix multiplication, if you want to know if it's possible, just write out the dimensions of each matrix in order, in proper order, and then you just look at the inside numbers. Are they the same? So here, if N and P are the same, okay, then matrix multiplication is possible. Also, dimensions, we can get another thing from this. How big will the result be? The result will be the number of rows of the first matrix and the number of columns of the second matrix. So those are the outside numbers. So if N and P are the same, then okay, it's possible. And how big will it be? It will be an M by Q matrix. The outside numbers tell you how big it will be. Inside numbers tell you if it's possible. Outside numbers tell you if what the dimensions will be of the result. So that's the easy thing. That's the easy way of remembering this. Just write out the dimensions of each matrix and then just look at the inside numbers. If they're the same, you can do it. And then the rest, how to do it, you just kind of the side one, the top one, line things up and everything as I just did. But this is the very easy way of knowing if it is possible or not. Okay, I hope that kind of makes sense. Does anyone have questions they would like to ask? about this process? Okay. So we'll go through some more practice with matrix multiplication in our next class, and then we'll do some examples or look at least one practical example of how this is used, and I'll explain why we care about this. And we'll talk about the null and identity matrices, why we care about those and why they're useful. And we will also have some time for review questions. So we'll get to those. Okay, so those are all the matrix operations those are the basic operations that you should know. So the transpose thing, adding and subtracting, multiplying by a scalar, and just take the outside number, multiply it by each value. That's the easy one. But then multiplying two whole matrices together, that's the more confusing thing that we just finished talking about. So next time, again, some review, and we'll wrap up with matrices. So if you are a Chinese student who is in China right now and therefore have trouble accessing Google stuff, stay after class and tell me. I need to know for certain who you guys are. And if you have other exam related questions and such, then also you can stay and ask. The homework and the survey or the form where you'll tell me if you have a roommate, and the practice midterm, the photos and everything, we'll have that back to you, ready for you a bit later today, sometime this afternoon. All right, thank you for listening, everyone. Goodbye. I will see you on Thursday.